Good morning. Welcome to this next lecture on complex variables. Before going full blown into another example using a branch cut, I wanted to do one more standard example. Okay, you will find these in many textbooks. So that example is this. Consider, so this is the next example. Consider I is equal to integral minus infinity to infinity e to the power ax dx by 1 plus e to the power x, with a being less than 1. A is a real number less than 1. Okay. Now, as usual, we will replace this with a contour integral. So this is a contour integral, and we replace x with z. So we have e to the power az dz by 1 plus e to the power z. Okay. Now, before proceeding any further, let's look at the roots of the denominator. Okay. What are the roots of the denominator? I have e to the power z is equal to minus 1, okay, which means I have e to the power z is equal to e to the power I pi plus I twice pi k, okay, and k can go from 0 plus minus 1 plus minus 2, etc. Okay. So now what do we have? We have a complex plane like this, and the poles are at, let's say, I pi, thrice I pi, 5 times I pi, okay, and again at minus I pi, minus I 3 pi, etc. So these are the poles. Now, as usual, I will choose so that I have this portion which is minus infinity to infinity e to the power ax dx by 1 plus ex, okay, plus other terms. So we'll see what those are. So let's see how the contour goes. So I come from minus infinity. There is no problem on the real axis, so I go straight to plus infinity. Then I close here, go up, and I go through this where it is twice I pi, okay, and I come back all the way to minus infinity, and then I close the contour. So if I initially set this to be minus r and this to be plus r, so I have the following portions. I have j, which is the closed contour integral, which is equal to the portion I want I, plus I have integral, okay, r to r plus I twice pi on all of them, limit r tending to infinity, okay, plus limit r tending to infinity integral r plus I twice pi here to minus r plus I twice pi plus limit r tending to infinity integral minus r plus I twice pi to minus r. So this is term 2, this is term 3, this is term 4. Okay. So let's look at term 2. Let us look at term 2. Term 2 is integral, okay, r to r plus I twice pi, limit r tending to infinity e to the power a z by 1 plus e to the power z dz. Okay. Now on this curve, z can be written as r plus it. Okay. Then dz, here r is a constant, so dz is equal to I dt. When z is equal to r, then t is equal to 0. When z is equal to r plus I twice pi, t is equal to twice pi. Okay. So now I have this is equal to limit r tending to infinity integral 0 to twice pi, okay, e to the power a r plus it by 1 plus e to the power r plus it into I dt. Okay. Now let me multiply the numerator by e to the power of minus r and denominator by e to the power of minus r. So I get limit r tending to infinity integral 0 to twice pi e to the power r a minus 1 e to the power of I a t I dt by e to the power of minus r plus e to the power it. Now as r tends to infinity, you can see that this goes to 0. So the denominator only e to the power it survives. In the numerator a is less than 1. So as r tends to infinity, this term goes to 0. So the integrand goes to 0. So this goes to 0. Okay. Next. That was term 2. Next is term 3. Okay. What happens to term 3? Term 3 is equal to integral r plus I twice pi into to minus r plus I twice pi, e to the power a z by 1 plus e to the power z dz. On this part of the curve, we can write z as equal to t plus I twice pi, so that dz equal to dt when z is equal to r plus I twice pi, t is equal to r, and when z is equal to minus r plus I twice pi, t is equal to minus r, and so term 3 is equal to integral r to minus r, okay, I forgot, limit r tending to infinity e to the power a, z is r plus I twice pi, dz is dt by 1 plus e to the power z, e to the power of r plus I twice pi. Now I have limit r tending to infinity integral r to minus r, okay, e to the power ar by 1 plus e to the power r I'm sorry, there's a mistake, there's an error over here, my mistake. This should be t, okay, this should be t. So this becomes e to the power at, and this becomes e to the power t into dt. Into e to the power of I a twice pi. In the denominator we have e to the power I twice pi, so that is 1. In the numerator we have e to the power I twice pi into a, so that comes here. Okay. So we now have term 3 is equal to, let's straight away put it, minus infinity to infinity e to the power at dt by 1 plus e to the power t into e to the power I a twice pi. Okay, but this part is my original integral that I wanted. This is I itself. Okay, so this is equal to I times e to the power of I a twice pi. Okay, now for term 4. Term 4 is equal to limit r tending to infinity integral minus r plus I twice pi to minus r, okay, e to the power az by 1 plus e to the power z dz. Okay. Now on this part of the curve we write z is equal to t z is equal to minus r plus it. So that dz is equal to I dt, and when z is equal to minus r plus I twice pi, t is equal to twice pi, and when z is equal to minus r, t is equal to 0. Then my term 4 is equal to limit r tending to infinity integral twice pi to 0 e to the power az a minus r plus it dz is I dt divided by 1 plus e to the power z e to the power of minus r plus it. Okay. Now what we have here is integral twice pi to 0 e to the power of minus ar e to the power of iat by 1 plus e to the power of minus r e to the power it limit r tending to infinity I dt. Now this goes to 0 because r is tending to infinity, and this numerator also goes to 0, and numerator multiplies everything. So this goes to 0. This goes to 0. So now we have, there's one problem that I had. The limits on term 3 are r in the denominator minus r in the numerator. Okay. So the limits here would be plus infinity here and minus infinity here, plus infinity to minus infinity. Okay. So this is minus I e to the power ia twice pi. So now what we have for j is I into 1 minus e to the power of ia twice pi, and that is equal to the residue. We are going to include just one pole, and that residue is at I pi. Okay. So we have to find the residue at I pi, residue of e to the power az by 1 plus e to the power z at z equal to I pi. Now we have seen before that if you have two functions p and q that are analytic, then we can find the residue by the numerator e to the power a z divided by the derivative of the denominator, which is e to the power z, evaluated at z equal to I pi, provided the denominator does not go to 0 there, so which it does not. So, this is equal to e to the power a I pi by e to the power I pi, which is minus e to the power I a pi. Okay. So, now what do I have? I have I into 1 minus e to the power of I a twice pi is equal to twice pi I times e to the power I a pi with a minus. Okay. So, here what do we do? I take I a pi outside, I get e to the power minus I a pi plus e to the power I a pi, okay, divide by twice I, multiply by twice I, that is equal to minus twice pi I e to the power of I a pi. This part is sine of a pi, sine of a pi. Okay. So, what do I have? I have I e to the power of I a pi sine of a pi into twice I is equal to minus twice pi I e to the power of I a pi. This is a minus over here. Okay. So, this gives me minus sine a pi. So, I have a minus over here. So, now if I cancel twice I, cancel the minus, cancel the e to the power I a pi, then I have I given by pi divided by sine a pi. That is the answer. Okay. Now, we will do the same problem using a second method called the method of path deformation. So, let me draw the complex plane. I have this integral which goes from minus infinity to infinity e to the power a x over 1 plus e to the power x dx. So, we start at minus infinity, we move through the origin to plus infinity. So, that is the entire integral. And my poles in the upper half are at I pi, thrice I pi, 5 I pi, and so on. So, now I will deform the path. Okay. Let us say I have deformed the path till here. I come down, I go around the pole, I come down, I go around the pole, I come down, I go around the pole, join up, go up the pole, go around, go up, go around, and then come back down here. All the while the end points are anchored, minus infinity and plus infinity, they are anchored. So in the limit what happens is I can deform it along a contour that goes on a circular arc at radius infinity. I come down, I go around the pole, I come down, go around the pole, I come down, I come to the bottom I pi pole and go up, go off to infinity and come back. Okay. Now what happens is that this function is poorly behaved only at these isolated singularities. Okay. Isolated singularities, and in between it is well behaved. So the integral that goes down between these poles and that which goes up again between the poles, they cancel out. Okay. So as a result, I will draw it here. As a result, I am left with merely counterclockwise integrals around isolated poles. Okay. Now let me just give an approximate proof of what happens on this portion of the deformed contour. Okay. I have integral over the CR e to the power AZ, okay, dz by 1 plus e to the power z. In here, as z tends to infinity, okay, z is moving on a circular arc r e to the power of I theta, so that 1 plus e to the power z is equal to 1 plus e to the power r cos theta plus I sin theta, and this is equal to 1 plus e to the power r cos theta e to the power I r sin theta. Now this is an oscillatory part, it does not bother us, but this here as r tends to infinity, okay, as r tends to infinity, this denominator blows up, and the numerator has a in it which lies between 0 and 1. A lies between 0 and 1, and so what happens is that this e to the power z as r tends to infinity will overwhelm the numerator, and so this integrand will go to 0. Okay. Exponent is a very rapidly increasing function, so this e to the power z will overwhelm e to the power az because of the limits on a. Okay. So this integral goes to 0. Okay. So now what are we left with? We are left with e to the power ax, which is originally from minus infinity to infinity. Okay. We are left with a series of infinite sums, okay, of residues at all the poles I pi, thrice I pi, and so forth. Okay. So how do we write this? We write this as, what is the residue at, let's say, I pi? The residue at I pi is e to the power az divided by the derivative of 1 plus e to the power z, which is e to the power z evaluated at I pi, which is equal to e to the power of I a pi by e to the power of I pi. Similarly, the residue at thrice I pi is e to the power of az by derivative of 1 plus e to the power z, which is e to the power z evaluated at thrice I pi, which is equal to e to the power I thrice a pi by e to the power I thrice pi, which I write as e to the power I pi. Okay, the same thing. So now what do I have? My j is equal to twice pi I into e to the power I a pi by e to the power I pi plus e to the power I thrice a pi by e to the power I pi plus e to the power I 5a pi by e to the power I pi, and so forth. So this is equal to minus twice pi I into e to the power I a pi plus e to the power thrice I a pi plus e to the power 5 I a pi, and so on. This is a geometric series. Okay. This is equal to minus twice pi I e to the power of I a pi 1 plus e to the power twice I a pi plus e to the power 4 I a pi, and so forth. So this is a geometric series with the ratio e to the power twice I a pi. Okay. So what does this do? This gives me minus twice pi I e to the power I a pi divided by 1 minus e to the power twice I a pi. Okay. So this becomes equal to minus twice pi I e to the power I a pi by e to the power I a pi into e to the power minus I a pi minus e to the power I a pi. Okay. If we simplify this, okay, this is equal to minus twice pi I. Now e to the power of minus I a pi minus e to the power I a pi by twice I is equal to minus sine a pi. So we have 1 by minus twice I sine a pi minus 2I, this is equal to pi by sine a pi. Now we do know that when we do geometric series, the ratio must be strictly less than 1, okay, e to the power twice I a pi, magnitude is just 1, okay. But in this case this series works. Okay. So with this I close this lecture. We will continue with branch cut examples again from the next class. Thank you.